So this morning for MIST's online seminar, we're very pleased to welcome Dr. Rosie Johnson. She is a lecturer in the Department of Physics at Aberystwyth University. She did her PhD at Leicester, finishing in 2018, and the focus of her research has been on using ground-based infrared telescope observations of hydrogen 3+ to investigate Jupiter's ionosphere. And she continues to specialise in H3+ observations, with a particular interest in the velocity in Jupiter's ionosphere. And I believe she's going to talk to us about that today. So over to you, Rosie. Thank you.
Yeah, great. Thank you. Thanks for that introduction. So yeah, today I'm going to talk about ionospheric flows primarily in Jupiter's polar region. So the focus of this is about infrared observations of Jupiter's aurora. And the reason why it's so important to observe Jupiter in the infrared is because we can derive the velocities, the H+ velocities from these observations. So I'll introduce you to the H3+ and to the infrared aurora and how we can derive those properties such as velocity. Which is, we can only get the velocities at the moment from the ground-based telescopes. So that's why this work's really important. So we'll look at some ionospheric flows, first in the northern aurora region and then in the southern aurora region. And then I'm going to finish the seminar with our plans for Jupidarn, which is a novel method to derive the actual velocity vector from the line of sight component. Okay, so here's Jupiter's infrared aurora. Some of you may be more familiar with the Earth's aurora, or you might be more used to seeing Jupiter's aurora shown at the ultraviolet wavelengths, but here it is in infrared. We've got an image of the southern aurora that's on the left there. Hopefully you can see my mouse. So yeah, so this is top left, an image taken by Juno-JIRAM of the southern aurora, and then this is some CRI-RES data that I've published in my 2017 paper. So this is the northern aurora. So we've got a few more features than the Earth's aurora. So we've got the main auroral emission, which in the south is kind of like an oval, but in the north it's more like asymmetric. It kind of looks like a kidney bean. And then equatorward of the main auroral emission, we have like the footprint aurora from the moons. You can kind of see a tiny bit there from the Io footprint aurora. Maybe you can see a bit more in the Juno image. And then poleward of the main auroral emission, we have all this really interesting and highly variable emission known as the polar aurora. So that's the infrared aurora. And the infrared aurora is mainly made, the emission is made from H3+. So H3+ is the simplest polyatomic molecule in the universe. And at Jupiter, since Jupiter's got a super hydrogen-rich atmosphere, it's made really quickly in Jupiter's atmosphere. So there's a fast reaction where you have ionization, and then that's followed by this really quick ion neutral reaction. So globally, H3+ is created through ionization by EUV. And then at the poles, we've got this extra precipitating energetic electrons, which can ionize the molecular hydrogen. So yeah, molecular hydrogen is ionized, and then H3+ can quickly react with with some more neutral hydrogen, molecular hydrogen, to make H3+. So in the auroral regions, the lifetime of the H3+ is kind of like on the order of tens of seconds, and then in the away from the aurora, like in the equatorial regions, it can be like about 1.6 hours. And that's where the H3+ is being destroyed through dissociative recombination. So because it's got like kind of a long-ish lifetime, that's why compared to the UV, sometimes the images can look not as crisp. But Yeah, so He plus spectroscopy. So it's, as you can see, this like schematic on the top right there, like it makes this equilateral triangle. So there's no permanent dipole, so there's no pure rotational spectrum. But as the He plus molecule like moves around, the centrifugal forces distort the triangle, make like a small temporary dipole, which causes row vibrational excitation, which is what we observe and measure. So we use, as I said at the start, ground-based telescopes, and we use these facilities because they have long slit shell spectrometers, which have a really high spectral resolution. And as I mentioned before, we need this high spectral resolution to derive the line of sight velocity of the H3 plus molecules. So currently we're not able to do that from instruments such as Juno-JIRAM. We can only do this from ground-based telescopes. So that's why this work here is really important to keep observing H3 plus from the ground. So in my work, I use IRTF, the NASA Infrared Telescope Facility, and I've also used VLT, the Very Large Telescope, which is in Chile. So we have these long slit shell spectrometers. Previously at IRTF, we had C-shell that got upgraded to I-shell, which has a much higher spectral resolution. And then we used to have CryoRes at VLT, but that upgraded. So we don't have CryoRes anymore, but the upgrades made the long slit slightly smaller, which actually is not that much of an upgrade for us because Jupiter is really big. So that's not ideal. But anyway, we use these instruments to observe Jupiter's aurora. So here's an image of Jupiter at about 4 microns. What we do is we put the slit of the instrument, so that white horizontal line there, that's the slit of the instrument, and then we sequentially move the telescope so that the slit like steps down through the auroral region, so you can like scan the whole thing. So that's another benefit that we have compared to like space missions. Like, yeah, they're there, they've got this really like high spatial resolution, but we've got the global picture. Like with iShell, you can take a scan of the aurora in like 20, 30 minutes, and you have that global context there. We can take an image of the whole of the day side, whereas like for space missions, they're going to take swaths through the aurora. So they've got to build up that image, so we can provide that global context for them. And then obviously depending on how much time you've been awarded to observe at the telescope. So from the new IRTF-iSHELL data set, we've got like 3-4 scans a night. So we're building up quite a lot of data to provide context for the Juno mission. And then obviously if we continue for the JUICE mission too. So here are some example of some spectra that you get of H3 plus from some observations in the past. You can see how the spectral resolution, also the breadth of the wavelength range has changed. So in the past, when we had iShell, we had like one emission line and then maybe another one there as well, depending on where you're observing. But yeah, kind of just 2 emission lines. And then for CryoRes, we had 4 detector arrays. So we had a broader wavelength range and really high spectral resolution, able to resolve a lot of lines. And then for iShell, we've got just heaps of orders, loads of orders. These are all orders, and yeah, loads of emission lines, which is fantastic for studying temperature. We can take the ratio of the emission lines to get the temperature, and also we can get some average velocities, use all the lines to get a more confident value for the velocity. So how do we derive the properties from H3 plus? So this emission line here, we would fit a Gaussian to every spatial position along that line. So for example, I've just chosen spatial position at row position 180, and then the Gaussian is the red line there fitted to the data, which are the crosses. So then the intensity is related to the height of that Gaussian. So then looking at Jupiter, say you had your slit like in the middle of the aurora, just like cutting through the aurora. So if you look at the emission line here, on the left-hand side, we're coming in from the dawn limb of Jupiter through one side of the main auroral emission, where it's kind of like narrow and bright, through the polar aurora to the diffuse side of the main auroral emission, and then off the dusk limb of the planet. And then if we fit a Gaussian to every spatial position along that line, you get this profile, this slice through the aurora. So you can see those features there that I just described cutting through the aurora. So that's the intensity for one position in the scan. But as I said before, we place the slit at the top of the planet and then scan down through the whole of the aurora region. So this means that we can map the intensity. So this is a map of the intensity for the VLT CryoRes data that I published in 2017. There's a number of labels on this projection to denote different regions of the aurora. And then also there's a dashed line here for the IO footprint. And also I've got a solid line here, which is showing the peak in infrared spectral intensity that I manually identified from that data set. The dot dash region is relating to some observations that Saladin took in 2003 that we'll discuss in a little bit. So as I've said, we can derive the line of sight velocity from the H3 plus emission as well. So this is where we determine the Doppler shift and relate that to the spectral resolution to get that line of sight velocity. So the velocity, the component of the velocity that's towards and away from the observer. So if you look at the spectral emission line compared to the dashed horizontal line, you can see that it's not completely like horizontal, it's Doppler shifted. And this is largely due to the planet's rotation, as planets rotating around once every 10 hours. So one side is rotating towards us and the other side is rotating away. But then we also have these additional Doppler shifts due to the ionospheric flows in the aurora region. So if we look at the slice here through the aurora region, you can see the intensity profile that I described before. So on the left-hand side is the dawn limb, and then cutting through one side of the main auroral emission through the polar aurora to the other side of the main auroral emission. And then the right-hand side of the plot is going off the dusk limb. So we've got a couple of reference frames that we use, and we don't just look in one reference frame, because to understand like the neutrals, the ionosphere, the magnetosphere, we need to look at it from more than one reference frame to get the full picture. So PRF, the planetary reference frame, that's where the solid body rotation of the planet has been removed. And that's a really useful reference frame because that's the reference frame of the neutrals, but also you can really in detail see those flows that are due to the aurora. So that black line there, you can see some strong flows deviating away from co-rotation. The H3 plus is not just going around with the planet there. And then the blue line is the magnetic pole reference frame, which is a reference frame. It still includes the strong rotation rate of the planet, but the magnetic pole has been set to 0. So now the velocities are relative to this magnetic pole there. So again, that's like one slice through the aurora. We've got a whole scan of the aurora, so mapped and projected that, which is what's shown here. So these are the flows that we've seen. So what are we? So like, what would we expect the flows to be? I suppose. So for those of you who are not familiar with Jupiter's magnetosphere, here it is. It's massive compared to the Earth's magnetosphere. The Earth's magnetosphere could kind of fit inside Jupiter itself, really. And then the sort of long-standing explanation of how the main auroral emission is generated is to do with the ionosphere coupling current system. And that keeps the middle magnetosphere like mostly co-rotating. So basically, Io produces like 1 ton per second of material, which is really quickly ionized, and that makes this like plasma torus that can co-rotate with the planet. That plasma is going to diffuse radially outwards because of bands between like centrifugal forces and thermal forces and Lorentz forces. So then so the plasma angular velocity falls away to conserve angular momentum. So then there's this like radial gradient in the angular velocity. So if you map from those field lines back then into the ionosphere, there's that reduction in angular velocity induces an equatorward electric field when you're in the rest frame of the ionospheric neutrals. So then you get this Peterson equatorward Peterson current. And the J cross B force associated with that balances out the ion neutral drag. So then the torque is communicated to the ionospheric plasma, the magnetospheric plasma by the sweep back of the magnetic field line. So if you look at this schematic here on the right, you've got the equatorial Peterson current there, and you've got your equatorial radial component, which is out here. And then they're joined together by like field aligned currents. So the current system is shown by the dashed lines, and then the magnetic field lines are the solid lines. And then the aurora is thought to be generated by electrons coming down this upwards field aligned current there. So this is the kind of like long-standing view of the generation of the main emission. That much evidence of field line currents or like any obvious inverted V plasma structures that are kind of associated with accelerated electron population. And papers such as like Bonford et al. Like 2020 have collated some of the evidence against co-rotation enforcement theory, kind of noticing, the inconsistencies between models, which are steady state and axisymmetric, and the observations, which tend to be quite asymmetric. So we don't have the full picture on how the main auroral emission is generated, but I guess what we were looking for in our velocities was maybe some signs of subrotation in the auroral regions to see if the co-rotation enforcement theory is correct, really. So in the past, previous studies mostly had taken like discrete positions in the aurora. None of these observations had like full coverage of the aurora. They were just like single or a couple of slip positions across the aurora. So they measured strong flows. Rega et al. Measured like in the main emission, they measured a really strong flow of like 3.3 kilometers per second. But when Stella et al. In 2001 measured the H plus velocity in the main emission, they didn't see quite as strong flows. It was like 1.2 to 1.5 kilometers per second, but it was showing this evidence of like a westward electrojet. So these is evidence of like subrotating flows. But interesting, they found some really strong flows in the polar region, which we'll get on to later. And Schofer et al. also found some strong flows in the auroral regions. They took an average and it was 3.1 kilometers per second, but that was at a slightly higher altitude than Rego and Stella had. But as I said, those were kind of discrete positions in the auroral region, whereas with the CRIRES data, we took a scan of the whole auroral region. So we were able to see in much more detail the flows. So if we start over here, this is in the planetary reference frame. So the rest frame of the neutrals. So we do see some subrotating flows on the dusk side, which is kind of basically in agreement with the understanding, the current understanding of the generation of the aurora, that long-standing view of the generation of the aurora. But then over on the dawn side at this local time, where the aurora is narrow and bright, there was like super rotating flows. Which, yeah, was kind of unexpected, kind of was expecting it to be sub-rotating. Although in the past there was potentially evidence that the super rotating flows were there. But yeah, it could be caused from a dynamically changing thermosphere, maybe like after a solar wind compression, or it could be like as the magnetic field lines that map to that part of the ionosphere, as they come around to the dawn side magnetosphere and they're compressed by the magnetopores, they increase in their angular velocity and go past co-rotation. So yeah, one of those. At the bottom there is a schematic trying to illustrate those flows. So on the dusk side, where I've labeled M2, we've got sub-rotating flows, and then M1, the narrow dawn bright side, we've got super rotating flows. Another region, oh no, that's not what I wanted to say. This was all assuming that the neutral atmosphere was basically boring and stationary, but maybe it's not. So in my 2016 paper, I looked at the mid to low latitude H2+ and found that it was co-rotating with the planet. However, more recently, Mellon et al. In 2024, so this paper from this year with some James Webb Space Telescope NIRSpec data, looked at the H2+ away from the auroral region and found that the morphology is not boring. It's super interesting. So this circle here is where the great red spot would be, like further down in the atmosphere. But the really interesting thing to note is like all the structure in the morphology. So now when I look at this, I just think, I don't think the velocity structure is actually as boring as maybe we thought in the past. And with higher resolution instruments, and maybe we'd be able to see, if we didn't take such a big average over such a large latitude range, maybe there is some detail in the velocities there. So that's away from the aurora. And we know that in the auroral regions, the neutral atmosphere, it's definitely not boring. So in the stratosphere, so this data on the left here from Cavalier et al. In 2021 uses the ALMA to take measurements of the line of sight velocity in Jupiter's stratosphere. And you can see that there's definitely some flows happening in the auroral regions, particularly in the south. There's some really strong sub-rotation. And also, if you were here for Royan's seminar last month, you'll know that about his work. So Wang et al. 2023, they took simultaneous observations of H2 and H2+ infrared emission. And then from that, they calculated this effective ion drift, and that's the relative velocity of the H2 and the H3+. So yeah, there's two asymmetric ionospheric jets, which are these blue bits here in Jupiter's northern aurora. And so they also drew a schematic which is kind of different to the one that I drew. So maybe agreeing on the more broad side on this right hand side here, but I think more in disagreement on the left here. But yeah, the neutral atmosphere for sure needs to be taken into consideration. Another part of the aurora that I find really fascinating and it especially interests me is this region that is supposedly coupled to the solar wind. And this is from some work started by Stallard et al. In 2003, when they put the velocities in a reference frame that was relative to the magnetic pole. So as I said before, we put the magnetic pole as stationary, and they found a region in the polar aurora that was stationary. So that's this region here that's bound by this black line. So these H2 plus in this dark polar region, they were stationary. And so Cowley et al. In 2003, they kind of put forward the idea that this meant there was a coupling to the solar wind. And they suggested that the configuration of Jupiter's ionosphere in the polar region looked like this, and that this region that kind of got the lines through it here, that was open to the solar wind. But others, such as Delamere and Bagnall in 2010, because that region mapped to the UV swirl region where there is aurora, they think it didn't really make sense to say that it was open. Like if it was open, then there should be kind of basically like not like really not much aurora there. But because there was some aurora there, they thought that maybe the coupling to the solar wind was through like a solar wind viscous drag. So as there would be, the aurora could still be there because there would be like small scale reconnection occurring during to twisting of the lines, like when in the Kelvin-Holtz boundary layer. But yeah, if it was as Cowley et al. In 2003 suggested, perhaps there should be no aurora in that region. So again, we didn't fully understand the mechanism that's coupling to the solar wind. And further work by Volk et al. In 2011 then suggested that, I guess kind of almost in agreement with Stahl et al. 2003, that the open region was in the middle from their modeling. So when we were looking at the Cryo-RES data, we were going to see if there was a region of stationary H plus ions, and we were, in the past, they were observed in the dashed dot region here, which is more in the center, but we found the stationary ions to be more coincident with the UV dark region. Excuse me. Which, could maybe suggest more evidence towards Cowley et al. 2003's theory of it being open magnetic field lines, because that area is more void of emission in UV and infrared. But until we have the information of what's actually happening, like if we have in situ sampling of the magnetic field that's coupled to that part of the aurora, then we would be able to determine the exact coupling mechanism. And since then, there's been further modeling by Zhang et al. In 2021, and their modeling showed like that the open flux could be stretched into a crescent-like structure poleward of the main emission, and that, I guess, that kind of agrees with that crescent-like open bit that we potentially observed with the Cryo-RES data. But as I said, the most rigorous way to test this will be to take the H3 plus observations and determine the line of sight velocity while the magnetic field lines at Jupiter are sampled in situ. And that's the plan that we had for the southern aurora. So this is some data now from IRTF-iSHELL taken of Jupiter's southern aurora. And this was taken on 2nd of February 2017. And this was during PJ, so Perijove 4. So this data we'll be able to work out, derive the line of sight velocity, and then compare it to the data taken by Juno to determine the plasma population along the magnetic field line. And maybe we can map from the ionosphere to the magnetosphere to find the source region, to understand the coupling between the ionosphere and the solar wind. So on this night, we had 5 scans of the aurora. I'm just showing scans number 4 and 5. So scan number 4 on the left and scan number 5 on the right. So 2 scans of Jupiter's southern aurora. So you've got the intensity at the top, and then we've got the line of sight velocity. This is just left in the observer's reference frame. So you can see the strong rotation rate of the planet there, where the limb is coming towards us, blue, and then rotating away, red. And then the bottoms are where the planet's rotation is removed. So you can see the strong flows in the auroral regions. These obviously, I think you can probably see that these are preliminary results that need to be fully analysed and mapped, but already some of the results are quite interesting. So this is a slice through the aurora, and here I was just kind of looking for some familiar flows to see if I could see any subrotation or perhaps superrotation. And we can see some subrotation here, like close to the main auroral emission, just poleward of it at this latitude. And then at the top of the aurora, we also do see a subrotation, but on this side, on this side, we also see a subrotation. So both sides of the aurora seem to be subrotating. And then at the bottom of the aurora, where we're getting quite subauroral now, there seems to be also a subrotation. But there is a lot on the dusk side. Here is quite close to co-rotation. So just having a quick preliminary compare to the northern aurora, it seems we see some familiar shapes with this dip down here, this subrotating, but the other side seems to be more closer to co-rotation. But as I said, I need to properly map this, and then once it's mapped, I can perform the final corrections on the velocity, the spatial velocities. So we'll be able to do a more in-depth analysis then. So finally, I'd like to introduce the idea of Jupidarn. I'm sick of trying to get a backronym for Jupidarn, so I'm just calling it Jupidarn now. So you might have heard of Superdarn, which is a chain of high-frequency coherent scatter radars, and they surround the auroral regions in both hemispheres. And the radars measure coherent backscatter from field-aligned ionospheric irregularities. So you get the Doppler shift in the backscattered signal, and then that can characterize one of the components of the E cross B drift. So the radar gets the line of sight velocity from the irregularity. So that's how fast the irregularity is moving with respect to the radar field of view, so like towards or away. And then, yeah, you can see that from these diagrams that the radars all have like overlapping fields of view. So that enables stereoscopic observations of the convection velocity of the ionosphere. So together the radars can determine the magnitude and directions of the flows in the ionosphere. And then the data is combined with a statistical model and then best fit images of the large scale convection pattern in the high latitude ionosphere is generated, which little plots of this on the right there, some recent examples. So yeah, you can see the data points there with the magnitude and the direction, and then the best fit of the model showing the convection cells. So having sat through a few Jupidarn talks, we realized we've got line of sight velocities and we've also got overlapping field of view. So that's where Jupidarn came from. So as I discussed today, we derived the line of sight velocities from the VLT cryo-res data. So this is that same data set that I presented just now before. So we had 6 scans of the aurora. So those are those 6 scans. And the duration of the scans was about like 4 hours, and Jupiter's rotation rate's like kind of about 10 hours. So over the observations, you can see that like Jupiter's aurora rotates like through our field of view. So we've got 6 scans. The first one starting at about CML of 180, and then last one going through to 242. So these have overlapping field of view. So instead of having multiple radars with overlapping field of views, we've got like one telescope and then Jupiter is rotating. So from the multiple overlapping field of views, we've got samples with different line of sight velocities at the same point, and then we can determine the magnitude and direction of the actual velocity vector. And that's going to make things so much easier to right now we have to interpret the line of sight velocity and then use diagrams such as this published by Royan, where we've tried to visualize what the actual flows look like. So Jupidarn will help make this easier and kind of determine whether or not our past predictions were correct. So I've been working with my colleague Tom Knight in Aberystwyth, and he's been instrumental in figuring out the mathematics behind Jupidarn, because in the first instance I assumed it was a bit of trig and spherical harmonics, but Jupiter's not a solid body, and there is a flattening where it bulges out at the equator, and it's an oblate spheroid, so the maths has become a lot more complicated than I could ever imagine, but apparently it is solvable, and Tom has done that, which is fantastic. So what we do, so we've got these 6 scans, and one assumption we have to make is that I mapped them accurately. Obviously there will be a small error in that, but we have to assume that we've mapped it accurately, so we can say that one sample, like 2 samples are taken at in fact the same point. And then we get all those samples and we put them into one big array. So you can have, in this big array, you could have a bin that had no samples in it, or a bin that has up to 6 samples. And anything that's too close to the edge, like we throw away. So if the pixel is overlapping the limb in any small way, we throw it away. So we can do the calculation with just 2 samples at the same point. So we can have 15 pairs from 6 samples, so we have up to 15 results at one position. And then from that, we remove the solid body rotation. And another assumption that we're making is that the flows are only moving within a plane and there's no vertical movement. The velocity is all parallel to the surface. Okay, so here are the results. I'd like to stress that this is a work in progress, and it's really exciting, but these are preliminary results. However, this is, even though it's not finished, it's a fantastic proof of concept, and I'm really excited about this because nobody's done this before. So on this figure, you can see this red boundary, and that's like the min, max, latitude and longitude, like bound of all our data. So there's these regions where there's no overlap, so we can't solve the magnitude or direction. And then as we move towards the center, there's more and more overlap, so we can be much confident about the data here. This data, this figure is an average of all our results. So I said, like, we can have up to 15 results in each bin. So in this first instance, as a proof of concept, we've gone for an average of the results. So this is, of course, making a big assumption that the ionospheric flows are not changing across these observations. And as the observations are several hours, like 4 hours of observations, the ionosphere probably will have changed in that time. But for this proof of concept, we have taken the average, and this gives us the average flows from this observation and gives us an idea of the bulk flows and the trends of the H3 plus velocity. But we do want to improve it, because we only need 2 samples to calculate the to conduct the calculation. So we technically could produce up to like 15 of these plots, but we need to determine our confidence level, and that's kind of based on the cadence. So if the samples are like close together in time, you have scan 1 and scan 2, then there's only like 30 minutes-ish between them. So then maybe we can be more, it's a more valid assumption to say that the ionosphere doesn't change as much in that time. But then in that time, the line of sight velocity wouldn't have changed that much. So you only get a small angle difference then to put into the calculation. And during the calculations, we take a cos of that angle, and a cos of a small angle is really large. So if we get any systematic errors, they get super exaggerated. So for the maths, you want the angle to be maximized. So you'd like want a sample from scan 1 and scan 6. But then that would be a really big time difference between those samples. So the actual velocity vector probably will have changed in that time. So then we might not be so confident about the results. So there's definitely a balance to be found there. There's like this playoff between maximizing the angle and keeping the cadence down, which is something that we're looking into. And then once we've got that like sorted and nailed down, then we're going to look into the 3D version. So then we can even consider the vertical flows, but we really need to check that the 2D version is all working first, and get this like play off between maximizing the angle and the cadence correct, because when you do that in the 3D, because there's more angles, it's going to be an even bigger problem. So I don't know, maybe there's not even a solution in 3D. We'll wait and see. But let's, I don't know, tentatively have a look at these preliminary results. Excuse me. So to understand this figure, we have this like sort of compass legend here. Like, so if it's pink, it's pointing north. If it's east, oh, sorry, that's chopped off a little bit. It's blue, and then green, south, west is yellow. And then the intensity of the color tells you the magnitude of the flow. So again, I'd like to stress that it is preliminary work, but even though it's preliminary work, and the general direction of the flows is not really going to change as we refine this method. The magnitude of the flows may change, but the general directions are not really going to change. So already these preliminary results kind of giving us an idea of what's going on, which is super cool, as this is the first time it's been achieved. So probably really tentative errors. These dash lines here, that's like where I'm saying this stuff here, that's noise, that's unphysical, I don't trust that. And over here, it's a bit too noisy as well. So one thing to say is that, like, yeah, it's a bit too yellow. There seems to be this sub-auroral westward drift, but I think that's because at the moment we'd solved it for like the surface of Jupiter, but we need to solve it for the altitude of the peak in H3 plus emission. And I think that would like, then that would kind of make things more co-rotating there. So we need to resolve that. So everything will be a little bit less yellow. But yeah, looking at the aurora, this has been a bit tricky for me to interpret, as obviously I had those ideas in my head from what I published and what others have published. But yeah, so this pink part here is moving northwards, and then we've got a westward flow here and a sort of east, like southward and then east flow here. So the aurora is kind of like flowing down and then kind of maybe diffusing out, and then it's kind of drawing in here and then up. So it's kind of going around-ish. So what my colleague Tom Knight is going to do is make a program so that we can drop a particle in and then it will draw the streamlines, which will be really, really helpful. Perhaps these views maybe help interpretation as well. So we've got east-west component here. As I said, it's probably a bit too strong, too much westward flow. I don't think it's going to ultimately be that. But looking at the north-south, that red bit going north, then that blue, dark blue part of the aurora going south, and then the other half of the aurora going north. So my arrows in my schematic maybe are the wrong way around, but maybe Royanne's arrows are closer, but you know what, it's probably too soon to say. Anyway, conclusions and future work. So previously, lots of studies, well, not that many studies. Some studies have identified significant ionospheric flows in Jupiter's aurora region, started off with discrete positions, and then we mapped it in the northern region. And now we're going to do the same for the southern region. And tentatively in the southern region, there's evidence of subrotation on the dawn side, but the dusk side seems to be closer to co-rotation. But we need to do the spatial correction for the line of sight velocities and then map it for further analysis. And then, yeah, Jupidarn is in progress. The preliminary results are showing some flows, which are interesting. But we need to get that optimization of the balance between maximizing the angle and keeping the cadence between the two samples down before it can be completed, so that we can look at more local time variations rather than that like big average. And then once we've got this 2D version down, then we can look at the 3D version and then finally include all the rest of the data from IRTF in it. So thank you so much for listening, and yeah, it'd be really great if anyone has any questions.